It was built to shorten time itself, a spacecraft engineered to cut the journey from Earth to Mars in half, from 9 months to 3. Every calculation, every weld, and every test pointed toward one singular promise: velocity. If Earth and Mars align every 26 months, then Starship was designed to compress the distance not by new physics, but by absolute precision. Orbital refueling, rapid relaunch, and Raptor 3 engines strong enough to erase the inevitable delays of deep space transit. But speed in the vacuum is not freedom. It is a profound friction against the invisible, unyielding wall of physics. A rocket that moves faster must contend with geometrically multiplying stress, increased heat, and the accelerating erosion of its safety margins. Every planned shortcut against the pull of gravity became a high-stakes wager with the constraints of heat, vibration, and time itself. The refined plan was direct: refuel Starship in low Earth orbit, then ignite the Raptor 3 engines at full thrust to achieve the 90-day transit. A mission architecture so inherently direct it appeared inevitable. At the heart of this system lay the revolutionary principle of orbital refueling, bypassing the prohibitive mass penalty required to launch a fully fueled Starship from Earth's deep gravity well. The design reversed the traditional logic, requiring the launch of a nearly empty Starship, followed by rapid propellant assembly in orbit via a tight cadence of tanker ships. This operation demanded dozens of Raptor 3 engines working in sequence, hundreds of valves, and thousands of welds, all operations precisely timed to the minute to assemble fuel in orbit faster than cryogenic boil-off could deplete it. The operational rhythm established at the Boca Chica launch site in Texas, where the harsh environment of wind, salt, and heat meet steel, was designed to turn the aerospace process into an organism of unceasing, perfect rhythm. The foundation of the entire accelerated Mars plan was the Raptor 3 engine, an extremely compact, violent, and efficient machine. Utilizing full-flow stage combustion of methane and liquid oxygen, the engine produced thrust exceeding 350 tons per unit, operating its combustion chamber at 330 bar, a pressure level surpassing any prior operational engine. Telemetry gathered at McGregor test facilities confirmed the engine achieved a measurable 10% efficiency gain over its predecessor, translating directly into the time saved for interplanetary travel. However, this gain in performance introduced an exponential rise in thermodynamic instability. At 330 bar, the combustion margins narrowed to mere milliseconds. A fuel ratio variation of just 0.5% could initiate oscillation, and at 1%, this oscillation could couple with acoustic resonance, generating pressure spikes capable of fracturing the injector plates. The structural logic of the Starship vehicle was equally unforgiving, demanding that the spacecraft shed mass without compromising structural integrity. Its stainless steel skin, an alloy designated 304L and only 3.6 millimeter thick, was chosen for its high tensile strength of 540 MPa at cryogenic temperature and its resistance to heat. While initially malleable under stress, the steel's survival under repeated thermal and pressure cycles is finite, allowing microfractures to form and stress to redistribute itself cumulatively, becoming an unlogged variable with every mission. The vehicle's thermal protection shield, comprised of 18,000 hexagonal tiles, relies on a thin adhesive layer that must resist thermal spikes exceeding 1400 degrees C. Any gap between tiles larger than 2 millimeters increases local heat flux by 15%, a tolerance that is tested and incrementally eroded with every launch and re-entry. In the engineering pursuit of the rapid operational cadence, the necessary inspection windows began to shrink, creating a fundamental paradox. Speed demands maintenance faster than maintenance can be reliably verified. Simultaneously, the vehicle's trajectory design moved away from the slow, fuel-efficient Hohmann transfer orbit toward a faster, higher-energy path that minimized coasting time. The Raptor 3 engines, fully fueled in orbit, provided the necessary velocity. An initial injection speed of 36,000 km/h later boosted by gravitational geometry to nearly 47,000 km/h at peak transit. Although this trajectory functioned perfectly in the vacuum of calculation, the high velocity introduced a severe hidden consequence. Upon arrival, Mars's thin atmosphere offered little drag, forcing the heat shield to absorb kinetic energy roughly double that of all previous deep space missions. The flaw in the accelerated plan resided not in the fundamental mathematics, but within the tightening of the margins. Late-stage trajectory optimization models, though confirming that a 45-day Mars transfer was theoretically possible, revealed that the required fuel volume exceeded Starship's maximum capacity by less than 2%. While orbital refueling was intended to compensate for this, the required precision for replenishment had to be within 0.5% of the total volume to avert fuel starvation during the trans-Martian injection burn. Furthermore, cryogenic methane expands by 1.6% for every 10 K of temperature rise. During long orbital exposures, temperature variations can reach 20 K, meaning the fuel mass at the moment of injection could deviate by 3% from the prediction, which was sufficient to shift the arrival velocity by hundreds of meters per second. This minor deviation entirely eliminated the margin for control correction. This was followed by a near miss during a critical engine endurance test, where a Raptor 3 sustained a continuous burn for 1,186 seconds. Telemetry recorded an oscillation spike at 1,070 seconds, where the amplitude increased by 3.2%. The root cause was revealed as a simple thermal failure. The fuel inlet temperature rose slowly, and the compensating software triggered microseconds too late. For a duration of 0.4 seconds, the combustion chamber temperature exceeded its tolerance by 67 degrees Celsius. Had the test continued for only 5 additional seconds, injector face erosion would have commenced, revealing the mission's safety margin to be a fraction of a second. The system's entire pattern was visible: speed reduced margin, thrust reduced cooling headroom, and optimization amplified stress. The black box analysis of the Mars acceleration plan ultimately exposed the core causal mechanism: synchronization collapse. The system's successful pursuit of speed was entirely dependent on perfect timing across multiple domains, yet space itself does not provide the single constant frame of reference required for such synchronization. When multiple tankers refuel a single spacecraft in orbit, they operate on slightly differing thermal cycles. Propellant in one tanker may be marginally warmer than in another, and pressure equalization across multiple transfers accumulates minor density differences, resulting in the total propellant mass after refueling fluctuating by up to 1.5% between missions. In Earth orbit, this fluctuation is negligible, but at the critical moment of trans-Martian injection, it proves fatal. Since fuel mass directly defines the available delta V, and delta V dictates arrival energy, even minor deviations shift trajectory phase angles by thousands of kilometers across interplanetary distances. The Raptor 3 engines exponentially magnified this constraint, operating near the absolute limits of material physics. At the operating pressure of 330 bar, the nickel alloy turbine blades expanded microscopically, altering clearances within the turbopump by mere microns. When the expansion rates differed between the fuel and oxidizer turbines, rotational synchronization inevitably began to drift. The longer the burn duration, the greater the divergence. Over a 20-minute interplanetary burn, the total impulse loss could reach 1%. On a 90-day trajectory, that 1% loss translated into a mission-ending deviation of millions of kilometers. Furthermore, records from test data indicated that the regenerative cooling channels within the Raptor 3, which carry supercooled methane, operated at flow velocities up to 20 ms. Should this cooling flow lag by more than 0.3 seconds during even minor throttling, The critical film cooling fails, exposing the metal to superheated gas. The material yield of the chamber begins at 1,250 degrees Celsius, while the combustion core temperature reaches 3,400 degrees Celsius. The architecture successfully achieved the 90-day theoretical transit window, yet every condition required absolute perfection. No wind, no delay, no microfracture. The system could tolerate no cold weld separation, nor a software desynchronization between 33 engines. The perceived reward of progress came with the full gravity of physical consequence. The faster the design attempted to leave Earth, the closer it arrived at the boundaries of physics itself. By late 2025, preparations finalized for the initial accelerated Mars attempt, designated TMV-1. This uncrewed robotic mission targeted the 2026-2027 launch window with an expected entry velocity of 7.4 km/s and a thermal load 1.9 times the previous maximum. The resulting numbers confirmed that the system was operating at the threshold of reliability. The initial test flight, TMV-1, successfully reached orbit. 6 tanker Starships completed the propellant rendezvous and transfer over 3 days, filling the tanks to maximum capacity. At T+76 hours, the engines ignited for the Trans-Mars injection, a precise 7 minutes and 14 seconds of burn. Telemetry showed no immediate anomalies, yet the process of refueling under variable sunlight had caused one side of the tank to be warmer by 3.6 K. This temperature delta created an uneven vapor-liquid interface that remained a fluid asymmetry locked inside the steel structure, the first unlocked variable in a system demanding perfect modeling. 47 hours into the cruise phase, a routine sun-pointing attitude rotation reoriented the thermal gradient across the fuel tanks, causing pressure in Tank B to rise by 0.09 MPa. The absence of convection in microgravity prevented gas from mixing evenly, allowing localized vapor pockets to expand faster than the venting system could equalize. These pockets pressed on internal bulkheads with uneven force, bending them by fractions of a millimeter. While finite element models predicted a safety margin of 0.3 millimeter deflection, telemetry later confirmed 0.29 millimeter. At T+5 days, Starship executed the first trajectory correction burn, TCB-1, firing 4 Raptors for 92 seconds. Though routine, the restart of thrust translated the residual stress from the tank asymmetry into vibration. The frequency of this vibration directly matched the tank's first harmonic mode. 18.6 Hz post-mission analysis later determined that this acoustic mode interacted with engine vibration harmonics, increasing the micro-crack propagation rate in one structural ring by 0.02 mm/hour. The cumulative yielding changed the interface's resonant properties, causing the harmonic frequency to drop from 18.6 Hz down to 17.9 Hz. The Raptor engine's second harmonic sat at 17.8 Hz, placing the system directly into a catastrophic resonance range. The reversal began at T+31 days during the mid-course correction burn. 46 seconds into the burn, oscillation amplitude doubled, and a pressure sensor in Tank B spiked from 7.0 to 7.3 MPa. Although readings returned to nominal within 2 seconds, the structural damage was irreversible. The inner wall of the common bulkhead experienced a cyclic load reversal. Tension shifted to compression in 0.1 seconds. This fatigue pattern initiated vibration-induced delamination of the internal insulating layer. With the boundary compromised, heat flowed across the 6 mm of stainless steel, causing oxygen ice to form and expand against the structure with a stress of 32 MPa. A critical near miss occurred at T+64 days during another trajectory burn. The differential pressure between the methane and oxygen tanks reached 0.42 MPa, close to the safe limit of 0.5 MPa. The control algorithm throttled back 2 Raptors, reducing the vibration and allowing the burn to complete. Retrospective review showed the mission survived by a margin of only 6 seconds. If full power had been held for that brief interval, the bulkhead would have buckled. The structural flaw stemmed from a fundamental human assumption. Engineers designed the bulkhead to maintain isolation based on the slow, low-intensity thermal cycles of a 6-month Hohmann trajectory. The high-velocity path, however, increased the thermal cycling from 4 to 11 times per mission, a frequency the initial design had never modeled. The time-dependent degradation had become the invisible variable. Material analysis of test articles later showed that cumulative fatigue growth rates were 3 times faster under rapid thermal cycling. The entire program was structurally modeling for duration, not for the intensity of its own accelerated cadence. The final catastrophic moment arrived at T+82 days during the last course correction burn. At 03:14:28 UTC, telemetry recorded a sharp pressure spike in Tank B, rising to 7.6 MPa, well above nominal. 1 second later, the bulkhead temperature gradient jumped 2.8 K. Although the burn completed successfully, internal sensors began showing a slow methane pressure decay 11 minutes later. This confirmed the presence of microscopic fissures that had begun the structural collapse. The mission ended at T+90 days during the Mars capture burn, designed to decelerate the vehicle by 4.1 km/s. 6 Raptors ignited smoothly until a loud vibration echo registered at the structural harmonic of 17.9 Hz. Methane tank pressure spiked to 8.1 MPa, while the oxygen tank dropped simultaneously. A sudden loss of signal followed, the capture burn failed, and the spacecraft missed the Mars capture window, forcing it into a fallback heliocentric orbit. The subsequent data aftermath confirmed the sequence. Repeated high-frequency burns induced resonance, thermal cycling degraded insulation, and microcracks propagated under cyclic pressure. The final burn exceeded the structural damping capacity. The core causal mechanism was thermal ratcheting. The high-velocity path layered energy faster than the structure could release it, resulting in a gradual rise in residual strain until the next ignition pushed it past the threshold. It was not an accident, but pure arithmetic. The investigators' final statement was clinical. The system achieved all intended performance goals, but the assumptions underlying its operation were incomplete. The true cause of the failure was speed itself. The initial loss prompted a full review of all high-velocity mission parameters. New constraints mandated thermal stabilization and cool-down intervals exceeding 4 hours between burns. The Raptor 3 engines were retrofitted with low-frequency isolation mounts to actively decouple engine vibration from the structure. The flawed common bulkhead was replaced entirely by a segmented titanium interface utilizing active thermal regulation, a change that added 320 kilograms of mass for the sake of restored reliability. Simulations of the new design eliminated resonance within plus 0.1 Hz. The lesson learned was simple and heavy. Acceleration multiplies everything: power, risk, and consequence. The failure confirmed humanity's capacity to engineer against distance, but not against time. The faster the design moves, the smaller the interval between cause and effect. The new doctrine was clear: faster trajectories demand slower, more careful reasoning. The next vehicle, TMV-2, launched 16 months later with the new safeguards and completed the transit successfully. Yet even that success carried its structural unease. Sensors still recorded a low-amplitude vibration at 17.6 Hz, below the danger threshold but hauntingly familiar. The data archives retained the pattern, the same frequency that had once destroyed TMV-1, waiting for conditions to align again. Every system carries its own echo. Every successful design conceals the ghost of its past failures. The accelerated route to Mars is not a victory over distance, but a perpetual encounter with the final boundary, the speed at which human control disintegrates. The final limit is always the one reached too late to see.